Okay, we are recording now, and welcome to Math 773. So now you can boast that you're taking the highest numbered course in our catalog. Uh,
Like not just math?
well,
In
for math, yeah. Yes, so now that should scare some people, or or make them think you're really a freak. Okay, so handouts. Okay. Schedule. So 2 items. Okay.
Thank you. Midterm exam. Oh man. What's up?
I think there are going to be some extras because there are 10 students in the class, but only
Maybe
8 of them will actually be here.
What do you mean? Syllabus?
Yeah, you should have a syllabus and a lecture schedule. Of course, all this information is on the class site, which I forgot to send to you guys. Oh wait, I did send it to you guys. Okay. All right. Okay. All right. Everybody has. Okay. Yeah, there should be 2 extras each. 1, 2, 3, 4. Okay, that worked out well. All right. So I haven't actually taught this class before. Taught 772 several times, but not 773. Although this material, taught most of it in various other classes. So I feel like it's not really much of a leap. So as far as the work, whereas for other classes, I have all of the notes lined up in advance. That's not going to be the case here because it's my first time teaching it. So I'll be writing notes as I go. So these are my notes for today. I haven't posted them on the site yet because what if I discover a mistake during class, which is bound to happen. And then sometime tonight, or after class, I will put these on the site after every class. So you'll have all that. As I've been doing in my other classes, some of you know, I record each class, so I'll put that up on the site after also. Okay, so with every set of notes, I will be assigning a few problems. Now all of you have a textbook. I sent that to all of you as a PDF. Okay, good. So after today's class, you can get started. I just assigned 3 problems. I'm not going to be dumping too many because I have to remember that whatever you do, I have to grade. So, so that's a limiting factor right there. And then, okay. All right. And then, yes, there will be tests. So, sorry. Midterm and a final. So on the schedule, I'll be doing my best to stick to the schedule. Sometimes there are deviations, especially if there's a hurricane or something. What?
Don't jinx us.
Okay.
I live on the water.
Okay, yeah. Okay, fine. And then, so this has the dates for the 2 tests. So I will announce homework due dates when I figure that out. I haven't even thought about that yet. I mean, I give you assigning problems every class, but that doesn't mean I'll be collecting them every class. I'll collect every so often, like maybe for every chapter, for instance. We're just covering a few sections today. We're covering 7 chapters altogether, 0 through 6. Yes, there's a chapter 0. Not sure why. Okay. Now, so as for what this class is about, largely Fourier transform and related concepts. That's a big chunk of the class. The first half of it is all about Fourier transforms, both continuous and discrete, because this is signal analysis for computational science. That's the name of the class. So really, for us, a signal it's going to be a function, a function of a single variable, a function of x or a function of t, and a Fourier transform is useful for understanding the frequency content of that signal. Like, is the signal largely confined to a limited range of frequencies, or does it have a very wide bandwidth? And the Fourier transform is an efficient way of determining that. So then you can do things like filtering out certain frequencies, or filtering within time instead of frequency. So we'll be looking at things like that. And then this later half of the course, like the last couple chapters will be, the last 3 chapters will be about wavelets. So wavelets are somewhat related to a Fourier transform. They have similar properties. But whereas a Fourier transform is concentrated only in frequency but not in space because of the uncertainty principle. They cannot be concentrated in both. But wavelets are as concentrated as possible in both senses. So that gives them some very nice properties there. So we'll be doing multi-resolution analysis involving Haar wavelets, which are the simplest kind of wavelets, and also Dobuchi's wavelets will be the very last thing. Besides signal analysis, the Fourier transform, wavelet transform are also of use in solving PDE, which is what I do. Actually, a lot of people in this department do. We also get out of this class a nice foundation for fundamental concepts, as you'll see at the very beginning, such as inner products, orthonormal bases, function spaces, things like that. Now, to make sure no one freaks out when you're looking at the syllabus, it says a prerequisite for this course is 771. I put it in there because that's what's in the catalog. None of you have taken 771, but that's okay. I'm not going to assume that you did. I have not taught 771, nor do I have any plans to in the near future. Usually it's either Dr. Ding or Dr. Lee who teach that class. So I'm just going to start from the very beginning of a book, which thankfully tiptoes into things. So don't worry, you not having 771, I can assure you, is not going to be a problem. Okay, so questions about the class? Of course, you guys never have any questions, but yeah, that's the thing for you to know being new here. No one ever has any questions.
So it's basically a pro forma comment to say, I've done my due, but I haven't calculated any time in for it because it's not necessary.
Well, I still put in time for it, but because hope springs eternal. Okay. Yeah, so I've dealt with this group before. So, all right. Let's see. But yeah, you can, in case you end up missing a day, you can see from this exactly what I'm going to cover. Just so you don't fall behind. Of course, you'll have the videos too to make sure you stay caught up. We're on a new schedule that instead of having 50 and 75-minute classes, we're here for an hour and a half. Not happy about that. So I can't imagine actually lecturing solid for an hour and a half. I mean, yeah, I've been doing an hour and 15 minutes for several years, but the extra 15 minutes I think might be the straw that breaks the camel's back. So we'll probably take some break somewhere around the midpoint, just so we all don't go nuts. Okay. So, and yeah, it's the first day of semester. It's been an exhausting summer, so I always like to come back for a fall, rested and all that, and I just have not. So
there was a pipeline course this summer?
there were a lot of things this summer, but that being one of them.
I don't know if you're kidding or being serious. Were you in the class or you weren't?
Yes, he was in the class.
Okay, so yeah, you was here.
Okay. Yeah. Well,
Well,
actually,
they're salty bodies.
but that's true. Yeah. Yeah. Yeah, all you saw was my screen. Actually, yeah. All of you. Well, yeah. We're in the class. So maybe you can experience that some other time.
No, call me. I had no idea who was in the class.
Oh, sorry. You were also taking it remotely. So yeah.
I feel really bad now. I didn't finish.
Yeah, but you weren't officially taking it either. So
That's true.
yeah.
I don't.
Yeah, it was a pretty draining summer. So, so right now I'm not quite in the swing of things. I'm not my usual effervescent self in class. So, just keep that in mind. But first day is something you just got to get through. Well, yeah, like in your classes, you just get through that first day, and then it's in spite of any technical difficulties that may occur, and then you trust that the second one can't be worse. So my
First class is always a trial run. Second class usually runs better.
yep. Okay, what? Okay. So I have here four pages of notes. My goal is to get through these 4 pages, and then we're done. So just to get the ball rolling. So I'm gonna recall something that I would teach in Calculus 3, and we'll hope that this chalk on this awful board is readable. Actually, yeah, I don't like the feel of this chalk.
I knew that was coming.
And I have better chalk up in my office, but it's all the way up in my office. So I'm debating now whether to put up a bit. Again, we are going to have a break later. So dot product, but really what we're interested in today is inner products. So the dot product is a kind of inner product. So now I'm gonna try to stick to the notation that's used in the book as much as possible for convenience, but sometimes on the board it might not translate as well. So I'm going to use lowercase and uppercase x's and y's. So I'm going to use that to distinguish. So this is my uppercase x. That now will look very different from my lowercase. That was burned by that before. So we have, so this is the notation that the textbook uses for vectors in R3, and then similarly for y. Also in R3. So there are many ways that different books use for writing the dot product or inner product. So this notation that we'll use with the angle brackets. So this is the inner product of x and y, that's also known as the dot product. And all that is you take corresponding components, so like x1, y1, x2, y2. So you multiply corresponding components and you add them up. Okay. So the dot product of 2 vectors is always a scalar.
Is that big X, big Y?
Ah, yes. Yeah, you're going to have to keep an eye on me. Yeah.
Did I get out outside?
No. They're angle brackets. Yeah. They just happen to look like less than or greater than signs, but they do not mean that at all. So, it's going to be interesting when I actually use some of them in the same equation. Okay. Now, so we also have the magnitude of a vector. And that's written in different ways. I'm going to use the double bars, my uppercase X. So a magnitude of a vector, we're talking about Euclidean length. So this is given so many names. Yeah, this chalk is too awful for words. Also known as the norm. Okay, so like I mentioned, there are different notions of magnitude, but we're pretty much going to stick with this one in particular, in this class. And the Euclidean length would just be the square root of the sum of squares of all the components. Okay. But the key reason why I bring this up now is you can also express this in terms of the inner product. It's the square root of the inner product of x with itself. Okay. So what this means is, if you have two entities, two vectors, and you're able to define any kind of inner product between them, then you automatically have a notion of magnitude or length. That's universally square root of inner product of a vector with itself. All right. Yeah. Yeah. I'm not going to keep using this chalk. I'm going to go to my office. And, yeah. That lasted 5 minutes. And see if that's any better.
What's really funny is that mathematicians being picky about chalk is...
He's so picky about it, but it does make a difference.
It makes a huge
I
difference.
used both of them because he showed me one day, and it really is like scratchy. Like it doesn't flow. It's so smooth.
Yeah, I once read the biography of the Natural Beautiful Mind. As a side note, it's amazing that the movie got so many things wrong. But they were talking about the Rand Corporation, giant think tank, collected the brightest minds everywhere. And one day they decided, they'd get rid of blackboards. And the mathematicians went on strike.
I hate chalkboard. I hate whiteboard. I like my document camera better because then I can face it. Right. I like it. Well, when it works.
When it works. I hate to admit it with the fact that I didn't know it.
I didn't either. That's the first time I've even seen it. And I figured it was from the computer. But it's weird because it hooks up through the computer to work. And that's just odd.
I think it's better.
Nice. That's usually how it works. And that's for every unit. You'll teach one class and then you'll realize things you either didn't say to your first class that you say in your second class, or...
I think this is a good first class.
Yeah, it's supposed to be a old camera.
No, it just didn't work. I mean, it's just like, lack of a better word, lecture is a presentation. It's a type of stand. I mean, it's just speech and how the audience reacts. It's meaningful. If it didn't work, go on.
So you didn't like show?
I did lecture.
Oh.
Far too beautiful. I like an hour and 30 minutes.
Okay. Whatever you said while I was gone was picked up and recorded. But
So now forever after, YouTube will know lectures.
So I should point out, in general, when I have a break in the middle of class, I will leave this running because what I found is, using QuickTime Player to record, lice together 2 videos, like a half hour. It's awful. Yeah, I don't know why. Maybe it's just my Mac or something. But so I just want to have one file to upload and get it done faster. So I'll just leave it running. So that way, like, yeah, if you have your break.
Class. I watched it on the computer. My husband came in and he was like, "Why are you just sitting there?" I said, "Well, I'm taking a break. Everybody else is taking a break." But there is no break. It just keeps going.
Yeah, because back then I would stop recording. And, yeah.
I did the same thing. Are you only going to take a break?
Yep. So now what I can do is, based on what we've seen here in R3, so the general inner product. Oh yes, this is so much better. I gotta remember to bring my own chalk in the future. But I'm gonna ask Miss Lisa to have somebody come in here and really clean this board. And if they can't for any reason, I may be able to switch to a different room. So I think 304 is available.
Nope.
No?
Matt 100's in there. They needed a document camera. So they had to be in that room.
Okay. But this is not a very general inner product. This is still Rn instead of R3. So we just define as, again, the product, and just add them all up. But we have to change things a little bit for complex vectors. So now if we have n-dimensional vectors whose elements are complex numbers, okay, so Z and W. What we do in that case is it's necessary to take the complex conjugate of one of the components. Now, here's one textbook that drives me nuts, is in every book I've ever used, when they've defined a complex inner product, they always take the conjugate of the first argument. So that would be the Z in this case. But no, these authors wanted to be different. So that's going to throw me off considerably. But I will stick with them so that hopefully it doesn't throw you guys off. But yeah, that's just it. No one can agree on anything. Well, you know how with the XY plane, so this is used mostly in trigonometry. You have a quadrants, 1, 2, 3, and 4. And everyone agrees on what is quadrant 1, 2, 3, and 4. Well, we don't have that in three-dimensional space. Three-dimensional space, you do have the first octant, where x, y, and z are all positive. But no one talks about octants 2 through 8, because no one can agree on how to define them. So we just don't bother.
Something in the future.
Something tells me they've already tried and failed. So.
Oh, they don't just.
Yeah. So just like we have different notions of spherical coordinates, and physics. Yeah. And when you have both physics and math majors in your class, it's kind of a problem. Now, the reason why I conjugate this is that now I'm going to take the magnitude of z. So that would be zj with its own conjugates multiplied together and add them all up. But when you take a complex number and multiply it with its own conjugates, you get the magnitude of that complex number squared. And therefore, you're guaranteed, okay, that's actually a greater than sign, or greater than or equal to, it's not an angle bracket, just to make sure. So that guarantees it's a real number and also non-negative, because figure, if you're going to find a magnitude of a vector, it ought to be, even if the elements of a vector are complex, the magnitude should be a real number, it should be non-negative. So if we don't conjugate this, we lose that guarantee. So that's why it's necessary in that case. As long as you conjugate one or the other, it's going to work. But we'll stick with the book's convention here. Now, just to make sure that everybody is up to speed on complex numbers, so z is like a plus bi, real imaginary parts of conjugate, it's just a minus bi. And then the magnitude is square root of a squared plus b squared, like Euclidean length in two-dimensional space. Okay. And if you were to carry out, if you were to take z and z conjugate and literally FOIL them, taking into account that I is the square root of minus 1, But you would get a squared plus b squared. So it all works out very nicely.
So when you were saying in the other books they do negative a plus b off?
Oh, no. What they do is they put the conjugate over here. Yeah. Fortunately, we all agree on what conjugate is.
That's what I was like.
Yeah. Oh, God, we didn't have that.
That's what I was like.
Complex analysis would cease to exist. But yes, what to conjugate, not how.
Okay.
It's in dispute. Okay. All right. So, and the thing is, so we might as well just stick with this definition because this is consistent with the real case. Because when you conjugate a real number, it's the same real number. So when if z and w are real, it just reduces to this. So that's what we use going forward is having the conjugate.
What happened to the W?
Oh, from here to here?
Yeah.
Oh, it went away because what is the root of the inner product? So this is the general inner product of complex numbers, but now I'm looking at a specific inner product.
Oh, okay.
Yeah.
I got
That was unfortunate.
it. Was.
Oh yeah, okay.
I got that one.
Okay. So that's just gonna stay down there all.
Oh no, I'll grab it.
Okay.
I'm like super Nazi about my pins. If y'all don't know, don't touch my pins.
So
I'm gonna grab it.
even the ones that have been abandoned. Yeah.
So what happened to the square root sign?
Hold on. So what?
The square root sign?
Yeah. Oh. Yeah, I need that over here.
Look at you.
Yeah. Okay.
Wow.
All right. Yep, and that was right. That was here in my notes the whole time, and totally forgot about it. Okay. So thank you for pointing it out. Okay. Yeah, I have to deal with square expressions just because I don't like to write out all square roots, and now you see why. Okay. Now, so one very important property of the inner product is it's called a bilinear function. So, okay. I'll just write down all the properties. Okay, so here we have the inner product of u and v, where u and v are elements of some vector space that's capital V. So this is could be any vector space. So vectors from Rn or Cn. Or in this class, we're largely going to deal with vector spaces where vectors are functions. And the inner product, a general inner product is written this way, where the dots are just placeholders. So this is a function whose domain is V cross V. In other words, pairs of elements from the vector space. And the range is complex numbers. So the inner product in general is a function that maps pairs of vectors to complex numbers. So there are many different inner products you can define. But in order to be able to call it an inner product, it has to have these properties. Okay. So you must have that the inner product of any vector of itself has to be a real positive number if V itself is non-zero. So the inner product of 0 with anything is generally going to be 0. So what that means is the inner product of any vector of itself is going to be non-negative. And because we want that to be, this is supposed to be the magnitude squared. So it only makes sense that that should be non-negative. Okay. Second thing, it's not commutative. It's almost commutative. So if you have an inner product of two vectors, and then you swap them, it's almost equal, but you have to take the complex conjugate. So in other words, if you're dealing with only real, it is commutative. Okay. Let's see. Third, what if you multiply a vector by multiply the first vector by a constant c? You're allowed to pull a constant. Okay.
Does it mean a constant multiplies only the v but on the other side?
W instead?
Like on the other side, does it multiply only v? Or
V times C.
Oh,
the c?
okay, so what's happening is here, c is multiplying only v. So in that case, we just pull out the constant. Now, can anyone tell me, using other properties, what if I have c multiplying w instead? I want to be able to pull it out again. But what do I have to do? You must take the conjugate.
But in most universes, if it's C multiplies V,
Yeah. And finally, we have linearity, or you think it's bilinear. So inner product is a function of two arguments. It's linear in both of its arguments. So you think it's called a bilinear form. So if I have a sum in the first argument, so u plus v inner product of w, I'm allowed to break that up as a sum of two inner products with w. That's quite convenient for simplifying expressions. And the same goes for the second argument. So really you can get this by putting other properties together. So that'd be uv plus uw. All right. So any function you can devise that has all these properties, you're allowed to call it an inner product. So we've seen like a standard inner product on n-dimensional real or complex vectors. We haven't seen any others yet, but we will. Okay. All right. And once you have this, once you have any inner product, you can define a norm of a vector v. It is always the square root of the inner product, whatever inner product you have, of v with itself. Okay. And then, once you have the norm, you can define distance. So the distance between two vectors is just the norm of their difference. Now, by virtue of being a vector space vectors can't be just anything. You have to be able to add and subtract them. So vectors have two fundamental operations: addition, which implies subtraction, and also scalar multiplication. So we already know how things that we can subtract. So if you can take a magnitude or norm of that difference, that gives you a notion of distance. That satisfies all the properties that a distance should have, like triangle inequality, things like that. Okay, and once you have that, I could define something else that's going to be important to us, and that is convergence. So you can say that, suppose you have a sequence of vectors. Call it vk. you can say it converges to a particular vector v if the limit of this distance between vk and v is 0. Because we prefer to deal with limits of numbers, not of vectors. But now we can define a limit of a vector in terms of limit of a number. So if this magnitude goes to 0, then the sequence of vectors converges to this vector.
So big V up top, little V down low. We're all big.
Yeah, I kind of got away from that, didn't I? But actually,
Those are fine to the left.
yeah, these are the same, also little. Yeah, these are vectors. Yeah. What's funny is a lot of books will use helpful notation for vectors, like they'll put a vector symbol above it, like an arrow, or they'll make them bold, which I often do in my notes. This book, it's like, we're not doing any of that. And I think even some people from faculty in the department will say, well, no, you don't need that. You should be able to figure it out from a context. Like, oh, sure, okay. Yeah, because why be helpful? And that left me torn as what to do, because, in my notes, in other classes, I always like to make vectors bold, for instance. But I figured, well, let's stick with what the book does, just for consistency, but I don't like it. Again, I didn't choose this book, so, yeah.
Who did?
I guess it was Dr. Zhu, who taught the course before I did. So now's a change from the other book.
Fallon's. Yeah.
Paul? Okay, yeah.
So really, the bookstore has a book that was out of date by.
Yeah, it was supposed to change back then, and it didn't. And, yeah.
One semester I can get, but
What?
having a book that's out of date by one semester is understandable, but multiple semesters? Wow.
Well, one change got missed, so yeah. Yeah, and I just found that out, so I was like, well, let's fix that later. Okay, so here are a couple other inner products, just to show you how unusual they can be. So let's suppose we have my vector space V is a space of all polynomials that have degree up to n. So I could write polynomial p, for instance, in terms of its coefficients. Oh wow, it's really burning through his class time. Probably not going to get through all these notes, but whatever. All right. So if we define the polynomials in terms of their coefficients, we could define an inner product in terms of these coefficients also. So what we'll do is we'll just take the coefficients. As long as we remember to conjugate one of them for the second one. So that right there is a valid inner product. Now there are other inner products that we'll see later for polynomials, but you can show that this satisfies all the properties that are required. But here we have n plus 1 coefficients in each polynomial. So this is actually, we're taking the inner product, standard inner product, on complex numbers of dimension n plus 1. We're just using it here. Oh, because what reason I mentioned earlier is that magnitudes are real numbers. So if you go back to those equations, okay, all right. No, because I don't want a situation where I'm taking the norm of a vector. Say, oh, what's the length of this vector? Well, it's I. we don't know what to do with that. So by conjugating, it guarantees if I take the inner product polynomial of itself, then these will be real numbers.
That's just the same with the W earlier.
Yeah, okay. Yeah, because it's because of that. Okay, another example of an unusual inner product. So this is just on my vector space is just going to be C2, so two-dimensional complex vectors. Okay. And so I'll let V have components V1 and V2, and W have components W1 and W2. So I could define the inner product as vector W1, W2 conjugated, because I conjugate the second one, times this matrix 2 minus I, and 3, and V1, V2. So it's a matrix times a vector, a column vector, which is itself a column vector, times a row vector, so the whole result ends up being a number. And it seems strange that this would constitute a valid product, especially because we have these complex numbers here. As long as the matrix here, whatever matrix you put in here, as long as it is Hermitian positive definite. So if I call this matrix A, we must have A equal to its Hermitian transpose, which is the same as the regular transpose complex conjugate. So as long as the matrix involved is Hermitian positive definite, then this will work as an inner product. And the reason for that is if I take the inner product of a vector of itself, then the expression reduces to this for this matrix A, which is guaranteed to be a real positive number if V is non-zero. And that's the definition of a positive definite matrix. So you can define any inner product using, on Rn or Cn, using a symmetric or Hermitian positive definite matrix. And that'll guarantee the positivity property. So that has the effect of weighting certain components more than others. Okay. All right. Questions at this point?
After that, there's all little V's and W's.
Yes, they are. Yeah. Well, I'm in a bind here because I know I should take a break, but I only have 37 minutes left anyway. 36 minutes. Yes.
Yeah. So what's the difference between the normal transpose and the Hermitian?
Oh, you take the complex conjugate. Yeah, so Hermitian is regular but conjugate. So just this break, because I only have 35 minutes left. I think I can handle that. And I don't want to fall behind on the first day. But again, we had the whole chalk thing and just talk about the syllabus and just being lazy. Okay, I want to talk about involving functions. Okay, so the function space, most of the time, for now anyway, is L2. And what you do is you specify a certain domain. In this case, it's just the interval AB, from a real number line. So I'm going to define L2 to be the space of all functions whose domain is AB to a complex number. So they're allowed to be complex valued, but the domain is real. And it has this condition that if they are if you integrate f squared on AB, that it's finite. So if a function's not allowed to like blow up, or have its integral blow up. Well, it's sort of, if a function goes to infinity at an endpoint, but slowly enough, so the integral still exists, that can work. But so this is called square integrable. So if the integral of a square exists. But notice I put the absolute value here, so it's the complex absolute value. That's important. Okay, so that's the space L2. Now, the standard inner products, I won't go through the whole derivation here because A, time, and B, not really all that interesting. But it's in the notes. The standard inner product on L2 is I take two functions from L2, f and g, and I can use a subscript L2 to indicate that this is a standard L2 inner product. And all it is the integral on AB, f of t, conjugate the second function, so conjugate g of t, dt. All right. Now, so what I'm going to do is I'm going to draw a contrast with a different space, lowercase l2. Now, so this is instead of a set of functions, it's a set of all sequences, infinite sequences, with coefficients that go both ways, negative and positive. So notice I have all the dot, dot, dot going in both directions. Okay, it was kind of weird, but and there's there's a condition similar to being square integrable. You must have that if you take the sum of the squares of all the elements of a sequence, it also must be finite. So the space capital L2 and lowercase l2 are very closely related. So here you have square integrable functions. Here you have square summable sequences. And its inner product, you have two sequences from lowercase l2 you take xn conjugate of yn. Now, I mentioned both of these side by side because I want to see the connection between them. What are we doing here? We are multiplying infinitely many corresponding components and adding them all up. Well, suppose I take two functions f and g, and I represent them by vectors. I evaluate the functions f and g at selected points in AB. So now I have vectors of a certain length. So now those are, you can think of those as elements of lowercase l2. I can take their inner products. Well, if I use more and more points, this sum becomes like a Riemann sum for an integral. Because what's an integral? An integral is the limit of a Riemann sum. So if I write out the definition, this is a limit as capital N goes to infinity of the sum of f of tj, g of tj conjugate times delta t, and delta t is b minus a over capital N. And tj's are equally spaced points in AB. So the standard inner product in capital L2 is the limit of a standard inner product in lowercase l2. Now, this is fleshed out a little bit more on page 3 of the notes that I will be posting shortly. I just didn't want to go through all the manipulations now. But I want to see why it makes sense that you can define inner product as an integral, because what's an integral? An infinite sum. Okay. All right. Well, now I hope that I can get through all these notes. Okay. But now things I don't have left.
Did you say the inner product of the capital L2 is the limit of
Of inner products from lowercase L2, because here I have a finite sum, but I'm letting the number of terms go to infinity. Yeah. So I have that does this explicitly defines the sequence. Okay. So this takes an idea of multiplying corresponding components and adding them up. It just takes it to the extreme. So we're working with these integral inner products quite a bit. Okay. Now, I mentioned here convergence, so I'm going to spend the rest of the time talking more about convergence. A lot of what we talk about involves approximating signals. So, like, when does a sequence of approximations converge to the real thing? Okay. All right. Now, there are 3 kinds of convergence that we'll be dealing with. Okay. So, the simplest type to work with is, and I actually kind of defined this already in a way, so for functions, convergence in L2. So what we say is a sequence of functions, which we'll call Fn, converges to a function f in L2, and you have to specify the domain. Don't forget to specify the domain, which is some interval AB. If, this is basically the definition I gave earlier, the distance between them using the standard L2 inner product, if that distance goes to 0. All right. But here's the interesting thing, though. Especially if a function f is not continuous, it's possible to have a situation where the difference between them, like your L2 norm, goes to 0, even though this function doesn't exactly converge to this function, like it's an actual equality at every point. And that's what takes me to the other notions of convergence. The second one is called pointwise. Pointwise convergence means that if you have a sequence of functions and you just evaluate them at a single point, t, and that converges at every point in AB, then that's called pointwise convergence. Now, convergence in L2 does not necessarily mean pointwise convergence. So, and I'll give an example, a counterexample to that pretty soon. But there's, I'm going to write this out, though, in terms of the definition of a limit. That's going to help when we talk about the other kind of convergence. Now, remember the delta epsilon definition of a limit? Or I guess also the epsilon k definition?
X plus delta. Is that what you're talking about? The limit is x goes to infinity.
Like that, yeah.
X plus delta, whatever.
You'll see. Yeah.
Minus f of x over
You might be jumbling things.
y.
Okay, I'll just write it out. So, So this means that for any point t in the interval, and for any epsilon greater than 0, there exists some capital N such that if little n is greater than 10, then Fn minus F is less. So this is like a definition of a sequence converging to a limit. So yeah, you would have seen it like in 441, for instance. Yeah. Okay. All right.
That's real analysis, isn't it?
Yes.
Yep.
Okay.
Yeah.
Yeah, good times. Okay. The third kind of convergence, which is the strongest kind, called uniform convergence. Now, I'm going to write this in terms of epsilon and capital N again. It's going to be a very slight difference. They're almost indistinguishable. So this says that for all epsilon greater than 0, there exists a capital N such that n is little n is greater than or equal to big N. Then Fn of t minus f of t is less than epsilon for all t in AB. So notice all I did was I moved one thing. I moved the for all t from here all the way over to here. And that's the only difference between pointwise convergence and uniform convergence. You might think, well, how on earth does that change anything? And it's kind of hard to decipher from all this gobbledygook up here, but I can say this in English. So pointwise, the value of capital N, it says, both definitions say there exists a capital N such that this works, depends on t. Whereas uniform convergence, there is one choice of capital N that works for all t in the interval AB. And that's very important because what can happen to pointwise convergence is you may have convergence that's faster at some points than others. So like for instance, suppose as you're approaching one endpoint of AB, maybe this capital N just keeps getting larger and larger, arbitrarily large. So then your convergence at that end of the interval is not as rapid. Whereas uniform convergence, there's a capital N that works for all t in AB. So this is like the strongest kind of convergence. Convergence tends to be more rapid than in the pointwise or the L2 case. Okay, so we're going to see cases like this where we have certain definitions to work with and very slight differences between them, and those differences turn out to be very important. Okay. So this is what makes math so evil, isn't it? Yeah. I don't know if this was covered in real analysis.
Oh, yeah.
2, okay, all right. Yeah. So, yeah, it's now you're probably like, well, we should have knew that back then. Okay. Okay. So first example, versus relate. Okay. So as an example, suppose I have this function, sequence of functions. So Fn of t is just t to the n. On the interval 0 to 1, where I don't include 1. Now, how do these functions behave? Well, for n equals t. And then next one is a parabola. And then as I keep going, as n keeps increasing. But the values of this function, if t is less than, also less than 1. And what happens is because it gets flatter and flatter, it's starting to look closer to 0 on more. So what we can say is this sequence converges to twice. on the interval 0 to 1, excluding 1. Because at 1, it's always equal to 1, so it's never going to converge to 0 at that point. But as long as we exclude 1, we're okay. But the thing is, convergence is not uniform. And the reason why is what's happening as you get closer and closer to t equals 1. Because what you want is, by the definition of pointwise, that for each t in 0, 1, there exists a capital N such that t to the n in absolute value is less than epsilon for all little n greater than or equal to big N. So what if we take this equation and solve it for n? Well, actually t is non-negative, so I don't need the absolute value. So I need n. So n's going to be, well, I have, I can take a natural log of both sides. So n is less than ln of epsilon over ln of t. So, oh, wait a minute. Greater than. Can anyone tell me why it flipped? Why did I have to reverse the sign of the inequality?
Is the natural log of t negative?
Yes. Yeah, t is less than 1, so its log is negative. So, what that means is I need to choose my capital N to be equal to natural log of epsilon, whatever that is, over natural log of t. And the thing is, t is getting closer and closer to 1. What's the log of 1? What? Yeah, 0. So the denominator is getting closer and closer to 0. So as t goes to 1, capital N is going to infinity. So capital N ends up having to get larger and larger to cover the whole interval. So because there's no upper bound on capital N, convergence cannot be uniform. So convergence over here to 0 and over here. It will eventually go to 0, but eventually means infinitely. Now, again, here's how a slight change in conditions turns out to be very significant. Let's suppose I chop the domain a little bit. I can say that convergence is uniform, not on 0, 1, but on 0, r, where r is less than 1. They might think, what's the difference? Well, there's always a gap between r and 1. R is some fixed value. So if I look over here, well, the worst case is when the t is equal to r. So at least n, capital N finally has an absolute ceiling. So that's why I could say convergence is uniform in that case. Okay. So this example really highlights the subtle distinction between the two. And that's why, as long as we don't allow ourselves to get arbitrarily close to 1, convergence is actually fairly rapid. Okay. Alrighty. Now, okay, I have good because I don't have much left at all. Okay, so a theorem about these types of convergence. All right, so a theorem says that, so if you have a sequence of functions that on a given interval AB, then that same sequence of functions will also converge in L2. But you is kind of convergence. L2 is actually kind of a weakest of the three. So it's no surprise that if it converges in a strong sense, yes, it will certainly converge in a weak sense. Okay. Now, what about the converse? What if you have a sequence of functions that converges in L2, doesn't converge uniformly? Well, since L2 convergence is a weaker form of convergence, it's no surprise that the answer is no. So the converse of this is false. So as an example, I'm going to define a function, fn of t, that's equal to 1 when t is between 0 and 1 over n, and it's equal to 0 otherwise. So what we can say is this sequence converges to 0 in L2 on the interval 0 to 1. But convergence is not uniform. And in fact, we don't even get pointwise convergence. And it's easiest to explain why we don't even get pointwise convergence, because there's always going to be some interval, however small, because notice it's t between 0 and 1 over n. So this interval keeps getting smaller and smaller as n goes to infinity. But there's always going to be some interval of some tiny size where this function is non-zero. So it will never converge pointwise to 0. And if it can't converge pointwise, it's not going to converge uniformly either. The definitions basically ensure that. But if you look at the L2 norm of fn of t, I can actually compute that. I'll compute the square, so that would be, that's the integral of fn of t squared. Now, we only have to focus on the part where it's equal to 1, so 0 to 1 over n, 1 dt. Well, what is that? That's just going to be 1 over n. So that's the L2 norm of fn of t, and that goes to 0 as n goes to infinity. So even though none of these functions converge, the sequence of functions does not converge to 0 in a pointwise sense, they're all non-zero on some slice. So it's behaving, something like this as n gets large. In an L2 sense, they still converge to 0 because where are they non-zero? On a smaller and smaller portion. And at some point that portion becomes negligible. So that's why convergence in L2 is a weak notion of convergence. But computationally, for numerical analysis, it's quite convenient, and that's why we still use it. Because what if you're only sampling functions at certain points? Then, if you have L2 convergence, then it's practically converged. But from a theoretical standpoint, it's a lot easier to work with. So that's one good thing about it. Okay, but beware that convergence in L2 is not all that it's cracked up to be. It doesn't mean what you think it means. It's like the Princess Bride. Use the word convergence. I don't think it means what you think it means. Sorry, I had to. Okay, so that's actually all I have to cover. I got through everything. It's amazing what you can do when you skip stuff, and you don't take a break. Okay, I picked out 3 problems from chapter 0. So the way the book works is there's a whole bunch of problems at the end across all the sections. So I just picked out 1, 3, and 6. Sufficiently tame. I did not go out of my way to choose hard problems. Maybe later. All right, but the thing is, I'm writing notes for next class day, and okay, so give us a whirl. So I'll next see you in a week. So you should ask questions about those problems then. I know you guys don't ask questions, but try. Okay, and I'll have these notes posted before I leave today, and also the video, but I'm about to stop right